Now we will see what are the properties of the joint characteristic function and the second joint characteristic function, how we could use them, and why they are useful at all. So the first thing we have learned is that the joint characteristic function has a one-to-one relationship with the joint distribution, and this is important because we can use this one instead of this one. Therefore, they fully characterize each other. They could be used instead of each other. Now, another thing we can do, we know, is that the joint characteristic function is equal to expected value of this function. And if we evaluate this function at omega 1 equal to omega and 0, so which means that replace this one by 0 and then replace this by omega, what we will find is that this expression becomes e to the power of j x omega, and mean of that, we have seen that this will become just the characteristic function of x of omega. So this is a one-to-one relationship with fx of omega. So you see that the marginal distribution, obtaining the marginal distribution in the characteristic domain is very easy. Just you replace one of them by 0, you get the distribution of the other one. Or you can replace omega 1 by 0 and find the marginal distribution for y. So, so if this is a 2D plane, let's say this is omega 1, this is omega 2. So if you look at the joint characteristic function on this line, you find the distribution of x. And if you look at it on this line, your distribution of y. And if you look at any other line, you will find a distribution of a linear combination of x and y. So, for instance, if you define a random variable z equal to ax plus by, the characteristic function of z, by definition, is mean of e to the power j omega times z. Now, if you look at this one, this is e to the power j omega a times x, and then plus omega b times y. Now, if you look at this one, the expectation of this one, if you compare this expression with what we have here, these two, you'll see that this is equal to the characteristic function of phi x y. Omega 1 is equal to omega a, and omega b is equal to omega 2. So basically, on a line which has some slope controlled with these a and b, if you look at this line, this is going to give you your distribution. So a linear combination in characteristics domain is easy. Just you replace the pair of omega 1 and omega 2, you replace it by a omega and then b omega, and then you get your distribution in characteristic domain. So obtaining the distribution of a linear combination should be easy in characteristic domain. So linear transformation is one of the advantages why we work in characteristic domain. So if you have lots of linear transformation, it's better to have the joint characteristic function. In that case, any linear transformation, easy to find the distribution. Another example of the usefulness of characteristic function is the Kramer-Wald decomposition. Now, if we have the joint distribution, if I have phi x of x and y of omega 1 and omega 2, then I could easily calculate distribution of this one, which is going to be equal to, you replace omega 1 by a omega and omega 2 replace it by b omega. So this is going to give me characteristic function of ax plus by of omega. So any linear combination. Now the question is that the joint density, so if you have the density of this one in many different lines, so if you have the density of this one, that means that the characteristic function on the line of, let's say, this is A omega and B omega, okay, so let's say if A is equal to 1 and B is equal to 2, so then here is, let's say, point A and this is point B, okay, so and then if omega is equal 1, so this is omega equal 1, you are here for omega equal 1.5, and for omega equal 0, for omega equal to -1, and so on. So your characteristic function on this line, on this line is going to be the distribution of this random variable. So if you have the characteristic function on all different lines, that means that you have the joint distribution. So this is the Kramer word distribution. So it says that if you have the distribution of any linear combination of two random variables, you have the distribution, the joint distribution. So the proof is now, if two random variables are independent, which means that f x and y, if f x y of x and y, if they are independent, this should be equal to f x of x times f y of y. So in that case, we want to prove that their characteristic function also could be decomposed, and this is very easy. So independence means the composability of either PDF, CDF, or characteristic function. So so you can prove this one very easily, because this is a double integral, and then if fx of y of x and y, and these two guys are single integral, this is single integral, and you can write the proof by yourself exercise. Now, if you this theorem says that any two independent random variables, their characteristic function of the sum is products, and we have seen that if you add two random variables, if they are independent, their PDF become convolution. Now, if you take Fourier transform, becomes product. Now, if you take log of that, ln of z of omega, you get ln of x of omega plus ln of y of omega. And you see that the second characteristic function of the sum of two independent random variables. So if you have two independent random variables, x and y are independent, the second characteristic function becomes sum of their characteristic function. So this means that independent entities, if they are added together, their second characteristic function becomes sum of the individual characteristic function. If the first characteristic function becomes product, and the second one, because you apply a log, becomes sum of them. Now, the derivatives of the second characteristic function, if you write a Taylor series expansion of the second characteristic function, there are moments, but they're not directly related to your distribution. They are indirectly, because you calculate the characteristic function and then you write the Taylor series expansion. The coefficient of the Taylor series expansion, they are called cumulants. Therefore, the cumulants of two added independent random variables is equal to the sum of the cumulants. So when you add independent random variables, their cumulants are added together, and the cumulants are not mixed. The cumulants of different order, which are the coefficients of the Taylor series expansion. So for independent random variables, the second characteristic function is the sum of the second characteristic function. That the first characteristic function is just the product, and the proof is something you can do. So because of additivity of the cumulants in literature, there's lots of papers that are using cumulants. For instance, if you want to verify two entities are independent, you can calculate individual cumulants and see if sum of the individual cumulants is equal to the joint cumulants or not. If they are not, that means that they were not independent.